Hi and welcome to our ICSE presentation on Linnaeus, our machine learning-based log classification pipeline. My name is Armin Catovic and I am a senior data scientist at Schibsted Products and Technology. Today I will present the main motivations behind various components and design decisions that went into making Linnaeus. It is our hope that some of the details presented here can be successfully applied in your own machine learning projects. First, I would like to introduce the rest of the team who were co-developers and co-authors of our paper. We have Carolyn Cartwright, a senior specialist in machine learning at Ericsson, Yasmin Gebreyesus, a software developer at Ericsson, and finally Simone Ferlin, a software architect at Ericsson. The work on Linnaeus started in the spring of 2017, during which time I was also employed at Ericsson. The main motivation behind Linnaeus is to reduce the time to find a fault. In telecommunications industry in particular, troubleshooting and fault reproduction are becoming increasingly important cost factors. This is true for both network operations as well as the R&D. Therefore, automating even a small part of the troubleshooting flow can yield significant cost benefits. The troubleshooting process itself is extremely complex and highly subjective. A lot of it is based on engineers' own experiences and gut feeling. However, when it comes to distilling troubleshooting into an automated system, software logs provide the most comprehensive data set and the ideal starting point. Due to telecom regulations and privacy requirements, our solution may need to be hosted on premises, it may need to be air-gapped, or sometimes deployed directly on the network hardware. Security requirements demand that we have full control of our software stack. So this rules out most commercial black box systems and also puts more scrutiny on open source machine learning frameworks, which may contain deeply nested dependencies. These requirements in turn put an upper bound on the memory footprint of our machine learning based solution, since we cannot think in terms of a near infinite pool of resources. And ideally, we would also like to reuse the same design or the same overarching solution across different parts of the telecom system, for example, in both radio as well as the packet core. So these requirements in turn have led to the development of our own solution that we called Linnaeus. And fundamentally, Linnaeus is just a supervised text classifier. It implements a standard natural language processing pipeline. Log snippets, which are just pieces of text, are transformed into a bag of words representation, which are then used as features, while the class labels, which are typically extracted from metadata in issue tracking systems such as Jira, are used as targets. The training pipeline uses a quasi-auto-ML method whereby a brute force search is applied through the estimator/parameter space to find the best fit model. Linnaeus is implemented as a set of Docker-based microservices. Training is done by a separate microservice that exports a compressed version of the NLP pipeline as well as the best fit estimator or the model. The inference or the classification microservice in turn imports this pipeline and slaps on its own inference-specific APIs and interfaces. So this gives us quite a bit of flexibility. In principle, we could completely swap out the current machine learning framework, which is based on scikit-learn, for something like PyTorch without actually having any code changes to the inference or classification microservice. We could also deploy the two things separately. We could have the training done internally in Ericsson R&D premises, while the inference could be deployed on an air-gapped system in a live network. The exported pipeline and the model from the training microservice could then be pushed out to the network periodically or as needed as part of the standard secure network update procedure. This separation of training and inference allows us better control over how we build our Docker images. After training, the pipeline is exercised while under a system trace. The output of the system trace provides a list of all the modules that are needed to run the pipeline. This list is then supplied to our final Docker file. Only the modules in this list are included in the build process. This ensures that we include only what's actually used and nothing more. From our measurements, this allows a tenfold reduction in Docker image sizes, which means smaller footprint and better security vectors. Now, since Linnaeus is a supervised text classifier, we require target labels or ground truth. While the ground truth is automatically sourced from metadata in Jira tickets, the data tends to be quite noisy. We are essentially at the mercy of each organization's ways of working. Metadata may be missing or it may be incorrect. Therefore, we implement our own log labeling tool called Linda. This gives troubleshooters as well as the data scientists easier and more explicit control over the data exploration process and the data labeling. We actually see tools such as these data annotation tools, as integral part of all production-ready machine learning-based systems. Finally, all the front-facing aspects of Linnaeus are exposed via REST APIs. Interface design was actually one of the most time-consuming aspects of the system. It requires careful balance between simplicity and flexibility. These, as opposed to small differences in precision and recall, ultimately determine the adoption of the machine learning-based system. Now, Linnaeus was successfully adopted across a range of log classification tasks, but one of the biggest applications in use today within Ericsson is within our component-based architecture platform, where Linnaeus categorizes the faulty log snippets into a specific software component. The idea here is that we quickly determine where the Jira or the bug report is meant to be routed to which software component that's responsible. Therefore, we save time and we save money. But Linnaeus has also been used in other classification tasks which are actually unrelated to log analysis, whereby the overarching architecture was actually reused, but the underlying machine learning objectives were completely swapped out. Now, you may have noticed that I spent next to nothing talking about the actual modeling aspects, and even the paper is very thin on these details. Our early experiments with the unsupervised log parsing did not actually yield good performance, so we opted for supervised classification. We then found that most of the off-the-shelf algorithms like naive Bayes and support vector machines and random forest work very well. Deep learning-based models do not outperform and are actually often worse than these simpler classical machine learning methods. And we have several hypotheses regarding this. Firstly, in the log classification tasks, as opposed to more natural language processing tasks, syntactic structures do not matter so much. So it is sufficient to treat log snippets as bag of words, and these classical models work really well with these kinds of representations. Also, the data is highly imbalanced. If we look at the number of faulty log snippets, they are very, very small, very few. And therefore, they are inadequate for deep learning algorithms to parameterize well. We see data engineering aspects as significantly more important than modeling. Data can be improved by slight modifications to the ways of working, for example, and we believe that these modifications are definitely worth the effort. Data annotation tools are also quite indispensable. There are a lot of off-the-shelf and commercial tools that can be used, but it is quite easy to also implement their own, like we did with our tool Linda. In the future, we also see greater need for example, weak supervision methods, perhaps as an extension to our data annotation tools. Engineering aspects, particularly in terms of integration with existing software and processes, are really the key. Not doing this correctly will result in low adoption rates and low reuse, and teams will begin to make their own implementations from scratch, which will effectively offset any benefits that are introduced by a system like this. Finally, it's important to start simple and small. Implementing a grand log classification system for the entire company or all the products and services is unrealistic. It's better to create something simple that can be easily molded or tuned to a specific domain or a context. And with that, I hope you have found this presentation useful. And if you have any further questions, please do not hesitate to get in touch with me or one of our co-authors. Thank you so much.
Okay, so welcome back. So it's my pleasure to be with Armin, Yasmin, and Carolyn. So let me go through the first question about their paper from Ibiza. So thanks. How much is your framework domain specific in a sense of type of data, diversity, changeability, and their semantics? Please.
Yes. So in terms of the framework, how specific it is, and the semantics, it's not very tightly coupled. So you can quite easily reuse it in a lot of different domains, actually. But then there's another question to this further down from Grace, and the classifier fairly domain specific. So if you train it, if you particular on logs from a very specific product or organization, then you can pretty much only use it for that product or organization. So now there is a possibility to kind of use some generic data and transfer products and projects, but that's sort of what you're using. So if you are using some fairly open source components, then different organizations, then absolutely you could do that. You could train it and you could actually deploy it in multiple organizations. Yes.
Okay. And there's this question from Taikia that I mean, it looks. I had also in my mind if this is software engineering for ML or if it's ML for software engineering or is something else, because that can be also an option.
Yeah, it's probably both, right? Because the way we developed it is and applicable in a lot of different use cases. But at the same time, the primary use case is machine learning for software development, right? To kind of speed up troubleshooting and log analysis. So it's both.
Okay, that's interesting. That means that there is an intersection or a bidirectionality that we need to take into account when we continue the discussion in this line. So there is another question from Jane. Do you think your observation that back-upwards approach generalizes? In other words, having made this observation, could you save yourself time on future projects by deciding to avoid DL approaches for certain problems?
Yeah, I mean, sorry, Carolyn, do you want to answer?
No, go ahead. Go ahead, Armin.
Okay. Yeah.
I know you feel strongly about this. Go ahead.
Yeah. Okay. You could, of course, use the deep learning. It's just that in these kinds of problems where you don't have these really syntactic structures like more natural language, where you have to understand entity relations and context a lot more, do work really, really well and analyze really well as well. So I would say in most these kind of log classification tasks, you could use bag of words and get really good results. And then maybe have that as a first kind of your solution, and then see if you can improve it with deep learning later. Yes. Carolyn, do you have some? I know you work more than I have, so maybe you have some additional comment.
I mean, the rule of thumb is to start easy. Is do see what you can get with the easy stuff, and this bag of words stuff is much easier up in no time. Whereas with the other one, deep learning isn't so. Yeah. And it's not necessary all the time either. It's just cool. It's very cool, but not necessary.
Yes.
So, and there is another question. Sorry to hurry up, but we have 40 seconds. Just try to increase the coverage. So from Silverio, it says only a few dozen logs represented true errors. How do you cope with imbalanced, noisy data?
Yeah, this is like the biggest problem that we have, right? Carolyn, Yasmin.
This was one of the biggest problems we faced, and to resolve this, we also had to avoid some of the components in order to have a balance of the sampling of the data. So we try to use components which have